for the invitation and introduction. I'm really happy to be here. And so, I think just 3 weeks ago, we had the Howard Georgi as a lecture, giving a lecture in this lecture series, and who's my advisor. So it really means a lot for me to be on the same stage. And I also just started a faculty position at Fudan University, so I feel obligated to promote my own institute. So for those of you who don't know, Fudan is the best university in Shanghai, and much better than Jiao Tong University, if you know what that is. Okay, jokes aside, and so this talk is based on these a few papers a few years ago, and also some current work with these people. So, and if you listen to any of my talk in the past few years, I hope there's still something new in this talk. So let me start. So I want to start with the very basics. So when we think about our field, particle physics, and how we have this a field, it really started when we tried to combine quantum mechanics and special relativity. Then we had no choice but to accept this bizarre theory called quantum field theory. And there are two very important consequences. So first, particle numbers are no longer conserved, so particles can be annihilated and created. And also relativity tells us that the mass is a form of energy. So to create heavy new particles, all we need is a high energy. So based on these, we have the following strategies for discovering new physics. So basically, we just need to build large colliders, which can go to a high energy, and then we discover new particles. So this strategy has worked really well in the past, and it's pretty much how we established the standard model, and which we are all very familiar with. So there are three parts: the wheel, the mug, and also the Mexican hat. And then, of course, the big question is what's next? So we are in a situation sometimes called Higgs and nothing else. So we found the Higgs, but we haven't found any direct evidence for new particles at the colliders. Then if we follow the same strategy, then the obvious thing to do next is to build an even larger collider to go to even higher energy. So maybe we can go up to around 100 TeV. But then, of course, such a collider would be very expensive. And unlike the situation in the past, now we don't really have a guaranteed discovery. So, I mean, it becomes more difficult to ask money to build such a collider. And of course, we also know a somewhat different strategy. That is, if we build a large collider, we can also do precision measurements. Then in that case, we can discover new physics indirectly. So if we go this route, and then the obvious next thing to do is to have a Higgs factory, because we found the Higgs. So which would be a lepton collider running at the center of mass energy around 250 or 240 GeV, and or even higher energy. And also, since we really don't know what the new physics is, it's important to have some kind of model independent approach. So then this standard model effective field theory, SMEFT, offers such a framework. And then, so naturally, these two things goes together. So I guess by now everyone is already an expert in SMEFT, but let me just say a few things for completeness. So of course, what we do is to take the standard model Lagrangian and just add more higher dimensional operators to it, and focusing on the those that conserve baryon and lepton numbers, then the order operators have even dimensions. So the first ones are dimension 6, and they are characterized by this scale called lambda. And then if this lambda is much larger than the electroweak scale, and also much larger than the energy at which we probe them, then basically this expansion works really well. The dimension 6 operators are much smaller than the standard model ones, and then the dimension 8 are much smaller than the dimension 6 ones. So we can, as a good approximation, we can just keep the first few terms in the expansion, just the standard model and the dimension 6 operators. And that gives a good approximation to the new physics effects around the electroweak scale. So what we usually do is to just write down all the dimension 6 operators and then eliminate redundant ones. And then we go to a so-called basis. And then depending on which operators we eliminate, we can go to different bases. And also the counting has been done. So for one generation, we actually have 76 independent parameters. And then for 3 generations, we have this very famous number, 2,499. So of course, this looks really scary. And obviously, we can no longer fit everything on the map. But the point is that usually we can just focus on a subset of the measurements, and then we also can focus on subset of these operators. So for instance, if we focus on the Higgs and the electroweak measurements, which is what we will do next, and we usually end up about 20 to 30 parameters. So it's still under control. So I mean, even though this 2,499 looks really scary, but in practice, we can work with a much smaller set of parameters and still do global fit. Okay, so that's SMEFT. So why do we want lepton colliders? And the obvious answer is that it's a factory, and not only for the Higgs, but also for a CW top. So it has a larger statistics, clean environment, and really means that it can do precision measurements. So there are basically 2 types of lepton colliders. So the circular and linear. So the circular colliders have the advantage of larger luminosity, and maybe more importantly, the circular tunnel can be reused for a hadron collider. So which can go to about 100 TeV. So this is kind of similar to the story of LEP and the LHC. And so linear collider the main advantage is that they can go to high energies, and you just need to dig a longer tunnel. And also it's easier to implement longitudinal beam polarizations and linear colliders, while it's much more difficult to do it in So of course, we are very interested in measuring the Higgs process. So maybe the most important process is the so-called Hex Coupling process, so E plus E minus 2 Hc. So its cross section is maximized at around 250 GeV. So that's why we want to run the collider at this energy. Got disconnected.
You're back now. You can just restart.
Okay. So I think I was on this page. So so the most important process is the Hex Coupling process, but its cross-section maximizes around 250 GeV, so that's why we want to measure at this energy. But there's also the so-called WW fusion process. Its cross-section increases with energy, so at high energy it becomes more important. And if the energy is large enough, then we are also open to a lot more other processes like TT bar H, which measures the top Yukawa, and also the those double Higgs processes, which can be used to measure the triple Higgs coupling, and so on. And of course, we can also measure the Z boson very well at the Z pole, and kind of like what the lab did, but with much larger luminosities, and also the W at the WW threshold and above, and also the top quark at the TT bar threshold, and also at high energies. Okay, so of course, with all these measurements, and so it's not enough to just have those measurements. We need to interpret them. So in that sense, the EFT framework is really good for lepton colliders because it offers a systematic parameterization of the Higgs and also other couplings. But on the other hand, lepton colliders are also very good for EFT studies, and at this point, maybe it's not emphasized enough as it should be. And so essentially, it's really because the high precision at the lepton colliders, then we can constrain the scale of new physics to be much larger than the energy where we probe them. And then in this case, the EFT expansion works really well, then everything works out. So it's it's really good for the EFT studies. On the other hand, the hadron collider like the LHC is really meant to be a discovery machine. But of course, we end up doing EFT studies at the LHC because, I mean, we do what we can. But of course, there's a very important statement called energy versus precision, which is that some operators have derivative couplings and they are more enhanced at higher energies. So it's really a advantage to measure those operators at the high energy tails in the distributions at the LHC. But of course, the problem is that because of the pattern distribution function, those events with high energies also tend to have low statistics, and then they tend to be measured poorly, and then this leads to all kinds of problems in the interpretation of the EFT. So this has been already extensively discussed in the LHC EFT working group, but here's a kind of oversimplified picture on what the problem can be and how people debate about them. For instance, what to do when the dimension 6 square terms becomes negligible. And also, by the way, this problem doesn't really get solved if you calculate the dimension 8, because when the energy and the lambda are comparable, then I mean all terms in the EFT extension can be equally important. I mean, then you also need to calculate dimension 10, 12, etc. So, I mean, we see that really, I mean, precision is the key here. So in that sense, lepton colliders are actually simpler. I mean, to a large extent, we don't need to worry about these kind of problems. Okay, so here's a possible timeline for the all the future lepton colliders, and well, I guess it's already kind of outdated. So this was from 2019, so everything is presumably shifted by 2 years already. I guess the main message is that I mean, I guess all of them are still alive, and but we don't know. I mean, nothing is confirmed. But I guess if we are lucky enough, we will be able to see maybe at least one in our lifetime. Okay, so of course there are numerous studies on EFT at future lepton colliders. So here I try to focus on the studies on global fits, and of course, this is still probably a very incomplete list, and I apologize if I miss any important work, but this is more kind of a reflection of my personal understanding on the field. So at first, the studies were done assuming the z-pole measurements are just perfect, and this is of course a reasonable assumption for current LHC measurements, given that the lab z-pole measurements are very precise. But whether this still remains to be true, and for future colliders, it needs to be tested explicitly. So this was done later in these studies, and it was also pointed out that so if we include the z-pole measurements and the corresponding operators, it's also very important to have the full EFT parameterization for the diboson events, A plus minus to WW. So otherwise, the EFT is not consistent. And this requires us to go beyond the usual 3 anomalous triple gauge coupling framework. And so we can also go beyond the tree level. So one important contribution at the one loop level is the triple Hex coupling. And it was shown that it actually has some we actually have some sensitivity by just measuring the Higgs-Rayleigh process to the triple Hex coupling, and it was later on implemented in global fit. And of course, we can also study the TT bar events and look at the top operators. And so this was done, for instance, in these studies. And also, if the energy is not high enough to reach the TT bar threshold, we can also probe these operators from their loop contributions to the Higgs and the electroweak process. And this was studied, for instance, in these papers, both in terms of the RG running of these operators and also the full one loop contribution. And so since the SNOWMAS study is going on, so some of us try to form a kind of team, which then they try to basically summarize the previous work and also try to improve upon those. So these are our current team members. So let me just say a few things about this, about our efforts. So our goal is definitely not to produce some official SNOWMAS results and then claim everyone else is wrong. I mean, this is definitely not what we do. On the contrary, we our goal is to just prepare illustrative global fit. By illustrative, we mean it's not the final result. It cannot be. And we want to focus on future lepton colliders, but also look at the combinations of hadrons and the lepton colliders. So we want to compare the different future lepton colliders on the equal footing. Although, I mean, maybe it's mission impossible because we all have biases. But we all have, I guess, we all have different biases. So as a team, maybe we are not, we are neutral enough, and then to do this. So we want to understand the role and impacts of different measurements like Z-pole, top threshold, and the effects of beam polarization, etc. And then these results can be very useful in terms of optimizing the run scenarios of these colliders. And we also want to understand the general issues and the subtleties in the global fit and the combination. And anyone who like to help is very welcome to join. You can contact any of us, but it might be best to contact our team leader, Junping Tian, who's also one of the organizers of SNOWMAS. And this is his email address. Okay, so I don't want to say too much on the technical details of the global fit, but let me just say a few things. So first, as mentioned earlier, so I mean, instead of this 2,499, and if we focus on the Higgs and the electroweak measurements, we usually end up with around 20 to 30 parameters. I mean, the exact number depends on the assumptions on the flavors and etc. But it's usually this, and so we can do a global fit. And so, of course, usually the results of the global fit is presented in terms of limits on the Wilson coefficients in terms of this C6 over lambda square. But of course, this can depend on the operator basis and the conventions, and it might be difficult to read for those who are not very familiar with this language. And there's also an alternative way, and which was proposed by this IC papers, so which is to present the results in terms of some effective couplings, and which is more or less straightforward, at least at tree level, but maybe with the exception of the HZZ and the HWW couplings, because of course, as we know, they can have multiple contributions as the standard model modifications to the standard model coupling, and also this kind of the anomalous couplings with different Lorentz structures, and they have different energy dependencies. And so the solution proposed by these studies is to simply define these couplings at the energy of the corresponding Higgs decay. So basically, this is just the definition. So they are proportional to the square root of the decay rate of the corresponding process. And so this is, of course, has a great advantage that it's very intuitive. It can be basically interpreted as Hex couplings, but this can also be a kind of disadvantage. I mean, the goal is kind of make it look like the so-called kappa framework as much as possible. But of course, this is not the kappa framework. I mean, in fact, there's a lot going on. I mean, there's all these things from the operators, and so it can be really confusing if you don't know what this is. And so a lot of our results are actually in terms of this framework. So might be better if I just make clear what this is. And of course, in the end, the most important thing is to present the results in with some fancy bar plots, maybe even more important than get your results correct. So, and here's one example. And so this was from the this study here. So as you can see, there are too many parameters to present it in a conventional bar plot. So we put it in a circle. And also we try to put the correlations among these parameters in the middle, even though it's kind of difficult to read. And but of course, the correlations are also a very important information. And well, I mean, this is too difficult to read. So here's basically the same plot, but in a conventional way, but just showing the Hex couplings and also the ATGCs. This is also quite difficult to read, but you can still see some of the main important messages. So first, if we look at some of the couplings and compare the high lumen LHC, which is the first column, and with the future lepton colliders, we can see that the future lepton colliders can do much better than the LHC for some of the couplings, and with about 1 order of magnitude improvement or even more. And also, it's what's kind of less obvious is that if we look at the impact of the ZPO measurements on the Higgs couplings, they actually have some impacts, which is shown in this lower panel, and let me just amplify it here. So basically, it shows the ratio of the bound you will get over the one that you will get, assuming the basically the electroweak measurements are perfect. So it shows how much your results would become worse if you don't get good enough ZPO measurements. So, and we can see that for this column here, so it's the circular colliders, and without the proposed ZPO run, and can see that the results can actually get significantly worse, and almost a factor of 2, and compare with the if we have the future ZPO run. And this is of course because of this kind of interactions that can come from some of the operators. So it's a contact interaction, and here if we replace the H with the VEV, then this is the modifies the coupling between the electron and the Z. So this can be constrained very well at the ZPO. But if it's not the case, then this interaction will enter the Higgs dwelling process, that makes your fate significantly worse. And so this is kind of an important message. It shows that in this kind of global fit, even ZPO measurements can be important for Higgs couplings, which is somewhat counterintuitive. But of course, and if we have runs at the multiple energies, and especially at lepton colliders, which can go to higher energies, and those also have beam polarizations, then in those cases, we can actually have more handles and to discriminate different effects. Then in these cases, and this effect is somewhat less important. So, and we don't lose too much by not having a ZPO run. And so if we have more handles, then we can also resolve this one from the other parameters. Okay, so another important aspect is the WW process. And and it's actually quite non-trivial to do the analysis, basically because the triple gauge couplings, as well as the additional EFT parameters, are sensitive to the differential distribution. So there's the question is how to extract the information from these distributions. So as you can see, for each event, there are actually 5 angles, 1 production polar angles, and the 2 decay angles on each side of the W. So we could try to do a fit to the beam distributions, but if we want to have a 5-dimensional beam distributions, we have too many beams. And on the other hand, if we try to look at only the 1-dimensional beam distributions, then we lose some information in the correlation among different angles. So either way, it's not the most efficient way of extracting information. And so that turns out to be a better way. And it's actually proposed a long time ago in the lab era and already used in lab for the same process, and they're called optimal observables. So basically the idea is that in the limit of large statistics and the small parameters, so basically we can only keep the linear contribution, then the best reach can be simply derived analytically. So, so in this case, we can write the differential cross-section like this. So this S0 is the standard model prediction. Then this GIs are the Wilson coefficients, and we only keep the linear term. And then also this is S1 is generally a complicated function of these phi angles. And then the inverse covariance matrix of this the EFT parameters is simply given by this formula here, and we can simply just calculate it. And also in practice, all we need to do is to measure these so-called optimal observables simply given by the ratios of these two, and then it has been shown that this will give us the best possible reach. And it seems really simple and kind of too good to be true. And it is kind of too good to be true because, I mean, this is all really ideal. And in practice, we need to worry about all kinds of things like detect acceptance, measurement uncertainties, etc. So in our current study, we try to look at these effects and see how much they can impact our study. So of course, we are still doing simplified analysis, but what we try to do, we try to look at some of the impacts of these effects. So so what we did was to first to implement some detect acceptance for the algo in jets and leptons, and also some smearing on the angles to mimic the measurement uncertainties. But for simplicity here, we only look at the production polar angle, but we give it a somewhat conservative uncertainty. So this is a large uncertainty for this angle. And also for IC, we also marginalize over the total rate and effective beam polarization, since these are also used to determine the beam polarization using the same process. And so these are the results. So basically, the first beam is the results from the ideal case, and then once we start to add these effects, then the results gets worse. But we can see that even when we add all of them, the effects is somewhat under control. So we have some kind of justification on this ideal analysis here. And so of course, in the end, everything will be in the full EFT framework. So we construct the full EFT likelihood from these diboson events. But here for illustration, I mean, here I'm just showing the results on the 3ATDC fit. And of course, in the end, it's very important that these results are further verified, especially by experimentalists. Then we can really be confident that this gives us a reasonable estimation on this the diboson measurements. Okay, so let me switch topics to the triple Higgs coupling. So of course, if the energy is large enough, and we can measure this with the double Higgs process. But if that's not the case, we can still look at its one loop effects in the single Higgs process, such as these ones. And the one important point here is that if we look at this diagram here for the Higgs-Jolyon process, then the threshold for this process is also the same as the threshold of this loop. So as a result, if you look at the sensitivity to the Higgs triple Higgs coupling of the Higgs-Jolyon process as a function of energy, the sensitivity is actually the largest near the threshold, and then it decreases as the energy increases. So if we want to be sensitive to the triple Higgs coupling, it's actually we actually want to measure this process near the threshold. But on the other hand, if we want to do a global fit, then it's very important to measure this process at least 2 different energies. Then that really helps separating this from other EFT parameters, which have different energy dependence. For instance, some parameters have energy enhancement, and so which would be opposite to this behavior. So this is kind of shown in this plot where we show the reach on the triple Higgs coupling as a function of the luminosities at 2 different energies. So one is the 240 GeV, the other is the TT bar threshold 350 GeV. And as you can see that to get some kind of sensitivity, we need to have at least some luminosity at both energies. And then, of course, the reach gets better if we have more luminosities. And so this is, of course, was already done in the past. So in our current work, we try to update these results with the new experimental inputs and also the updated diboson analysis. And so the results are qualitatively the same, but there are still some interesting findings. So one is that because of this sensitivity to the energies, and it's actually, I mean, a small difference in the run scenarios can make quite a non-negligible difference. For instance, having the run at 240 GeV is better than 250 GeV, and for constraining the triple Higgs coupling. And also similarly, 365 is GeV is slightly better than 350 GeV. So you want to, I mean, you want the difference between them to be as large as possible. So in that aspect, the circular colliders is slightly better than the linear ones because the optimal run energy for circular colliders at 240 GeV. Of course, for linear colliders like the ILC, once the energy is large enough, for instance, at 500 GeV, then we can measure the double Higgs process. Then combining the two, we can get a much better result. So another interesting result is that, as mentioned earlier, this the Z-pole measurements can have an impact on the Higgs coupling. And here we found out that it also have an impact on the triple Higgs coupling in this framework. So this is, again, I mean, because of this kind of contact interaction. And when we look at the FCC EE scenario and then just scale up the Z-pole uncertainties, then we found that the bonds on the triple Higgs coupling actually gets worse, not by much, but it's still kind of non-negligible. And this is somewhat counterintuitive because this coupling has a large energy enhancement. So naively, we thought that I mean, it's very easy to separate the effects of these two. But it turns out the effects are still non-negligible. So this is quite interesting and a bit surprising. So we want to investigate it further. Okay, so we can also look at the top operators if we measure this TT bar process, and as pointed out, for instance, in this study, so if we want to do it in the EFT framework, then there are actually a lot of operators that we need to worry about. So in addition to those that modifies the top gauge couplings, we also have those that generates dipole interactions. So this cannot be neglected since the top is heavy. And also this kind of 4 fermion interactions for the that generates the EETT contact interaction. And the one important result pointed out by this paper is that if we just have the top threshold run, for instance, at the FCC EE, we can have the run at 350 GeV and also slightly above it, 365 GeV. Then it's actually very difficult to separate the 4 fermion interactions from these ones. And as you can see, I mean, the correlation matrix is basically a 1 between some of the operators coefficients. And of course, this can be easily understood if we think of, for instance, some kind of Z prime model. And when we compare its contribution with the one from the standard model gauge bosons, then of course they have different masses. And if you measure this process at 2 different energies, then you can easily separate these. But of course, the problem is that we don't always get to measure it at 2 different energies. And then, for instance, in circular colliders, then I mean we can, maybe we'll have to accept this this degeneracy. Then of course, whether that's a big deal kind of depends on the personal preferences. And of course, maybe we don't even have a run at the top threshold. And so below the top threshold, we can still probe these operators from their contributions, loop contributions in the Higgs and electroweak processes. And but then again, the problem is that if we want to do a global fit, then then include these loop contributions, there'll be more parameters. Then it's more difficult to close the fit. So here's one example where, for instance, this kind of dipole operators can have a sizable contribution to the H gamma gamma vertex, and it's also not very well constrained at the LHC. So without the top threshold run, if we consider its contribution to the Higgs process, then naively it will make the bond on the H gamma gamma coupling much worse. So basically, there's a large degeneracy between those, and then in that sense, maybe having a run at the top threshold will be very meaningful in terms of trying to discriminate. I mean, these operators that would otherwise be very difficult to separate if we just have the Higgs measurements. Okay, so we could also look at the dimension 8 operators. So naively, we would think that because of their large energy enhancement, it might be a advantage to look at those at the LHC, because the LHC has larger energy. But again, the problem is that for the LHC, the events with large energy also tend to have low statistics. So the problem is even worse for dimension 8 operators. So here's one example from a CMS study here on the Victor boson scattering. So they put some bounds on some of the dimension 8 operators. And also one motivation to study these operators is that they exhibit so-called positivity bounds. So assuming we have a UV completion that's consistent with some the principles of QFTs, and only some of the operator coefficients are allowed, which is shown by this green region pointed out by this study here. So of course this all looks good, but until we look at this the scale here, then in this case the bounds on the scale of new physics is comparable or even much lower than the energy reached on the events. Then in this case, basically the EFT expansion breaks down, and then I mean this result can can be somewhat problematic, and so it seems that in general, if we want to probe these dimension 8 operators, it's really important to have both precision and energy. And then that seems that a very high energy lepton collider can have advantage in this case. And an alternative strategy is that to find some special process where the dimension 8 operators actually gives the leading new physics contributions. And well, I mean, this isn't really related to the previous the global fits, but it's just some interesting study we did recently that we found that the diphoton process is actually somewhat special, that the leading contribution comes from dimension 8 operators, and then we can probe them in a somewhat robust way at the lepton colliders, even if the center of mass energy is not very large, and also probe the positivity bonds that are related to this process. Okay, I guess I finished slightly earlier. So to conclude, I mean, here's just a few simple messages, kind of like slogans. So to a large extent, the precision measurements is more or less becoming the future of our field, at least for the next 20 or 30 years. And especially it's important to measure the properties of the Higgs boson. And so lepton colliders are basically Higgs factories that are really great for this purpose, but it's also factory for the CW top and can measure the properties of these particles very well. And for these precision measurements, then the SMEFT really offers an ideal framework to study these measurements. But of course, as we know, it's not everything. And of course, we can wait for maybe 20 or 30 years and until we have the real data and then apply the same analysis again. But of course, in the meantime, we still have a lot to do. And for instance, we can consider more measurements and on other dimension 6 operators. For instance, 4 fermion, some of the 4 fermion operators can be probed very well also at lepton colliders. So we can also consider more loop contributions. And so it was pointed out that for some of the dimension 6 operators, even though they are, we can probe them at tree level, the loop contributions can still be negligible. So it's important to include these effects. And as just mentioned, we can also go beyond dimension 6. But in general, I mean, we know that there are a lot more operators at dimension 8. So I don't know, maybe it's impossible to do a global fit with the dimension 8 operators. So we can also think about going beyond the framework of SMEFT. For instance, there are some studies on the so-called Higgs effective field theory, HEFT, and also different parameterizations of SMEFT, like geo-SMEFT. And so these are all very meaningful directions to explore further. But perhaps one general problem with all of this is that I mean, they also kind of make your analysis more complicated. And then at some point, I mean, once we have too many parameters, then it'll be difficult to close the fit. Then, I mean, what we do in that case then is somewhat kind of open question. So before I finish, I want to say a few things about the history. So in 1875, a young Max Planck was told by his advisor not to study physics because there's nothing left to be discovered. So obviously Planck didn't listen. So he went from a handsome young guy to someone like this. And in 1887, Michelson and Morley did their famous experiment to find ether, which was the new physics at that time that everyone believed to exist. And of course, they didn't find it. So the same Michelson also had the following sentence. So our future discoveries must be looked for in the 6th place of decimals. So it was widely thought that this was a statement basically saying that new physics is dead, and which turned out to be horribly wrong. But maybe he already had the wisdom at that time to realize that precision measurements is a great way to discover new physics. I mean, this very experiment they did was a precision experiment, and I mean, it started a revolution of modern physics. So I guess, well, I mean, where history repeats itself, I guess we'll find out eventually. Okay, thanks.